Hello everyone, welcome to the channel Statistica Hub. So in the previous lecture we have completed inner product spaces and we have also done some introduction of orthogonality. Okay, so now in this lecture we are going to discuss all the things that comes under orthogonality. So let's see it. Okay, so orthogonality. So what is in the orthogonality? So for that we have a V which is my inner product space. Okay, and this is not IPS, right? This is inner product spaces, and there are two vectors which are lying in this inner product spaces. Let's just consider those vectors are U and V, which belong to inner product space V. Okay, now these vectors are said to be to be orthogonal if the inner product of them would be equal to 0. Okay, and you can also say this, that if we represent these two vectors in the vectors format, then if u dash v is equals to 0, okay, then we will say that u vector is perpendicular to v. Okay, u is perpendicular to v, right? And if it is perpendicular to v, so it is obvious that it would make these two vectors would make an angle of pi by 2, that is 90 degree, right? So let's see it. Let's take an example of it, that how we proceed this in a question. So I'm taking two functions here, which is sine t and cos t. Okay, and they are in vector space of continuous functions, which is from minus pi to pi. Okay, now in this we want to know that whether these functions are orthogonal or not. So for that we have to find the inner product of these two functions, that is sine t comma cos t. So we are going to find the inner product of these functions, and if the inner product is equals to 0, then we will say that the functions are orthogonal, right? Okay, so let's just check it. So my limit is going from minus pi to pi. So minus pi to pi sine t cos t into dt. So the integration of this, we all know that the integration of this would be 1 by 2 sine square t. Okay, I am written direct because I know that if I'll just consider sine t, considering one thing as something like z, then other thing would go to dt, dz. Okay, so this is 1 by 2 sine square t. This is a simple integration, and which the limit is minus pi to pi. Now we know that the value of sine pi is 0 and sine minus pi is also 0. So the resultant comes here is 0 here. Okay, so the inner product of sine t and cos t is equals to 0. So from this we can say that these functions sine t and cos t are orthogonal functions. Orthogonal functions. Okay, so these are orthogonal functions. Understood? So taking out the inner product of any two vectors or any two functions, any two matrices, whatever you want to find out for, you just have to check that whether the inner product is 0 or not. If it's 0, they are orthogonal. If it's not 0, then they are not orthogonal. Simple as that. Okay. Now let's consider and another example for subspaces. Let's just say that I have W1 be the subspaces which is generated by these two vectors 1, 1, 2 and 0, 2, minus 1. Okay, and W2 is my another subspace which is generated by let's take minus 5 to 1. Okay, minus 5, 1, 2. Let's just take that minus 5, 1, 2. Okay, and we whether these are orthogonal or not, we need to check that. Orthogonal. Okay, and remind these that these are my subspaces. Subspaces. Okay, so if these are subspaces, they can be written, and these are generating, these vectors are generating subspaces. Okay, so these can, every vector in these subspaces can be written in the linear combinations of these vectors. because they are the generating set here, right? So for the W1 subspace, every vector which is in the W1 can be written in the linear combinations of these two vectors. So it would be lambda 1, 1, 1, 2 plus lambda 2, 0, 2 minus 1, where both these lambda I belong to R, right? Similarly for this one, W2 subspace, every vector in W2 can be written in the linear combination of this vector because this is the generating set of the subspace. So here it can be written like lambda 5, sorry, it is minus 5, 1 and 2, okay, where lambda belongs to R. Okay, so these are my two subspaces here, and every vector in them can be written in the linear combinations of these vectors. So let's just say that I am considering this as A and this as B. Okay, we have considered these two vectors. So let's just find out this A dash B. This A dash B, we are going to consider that. Okay, let's just find that out. If I'll do A dash B, so I'll write those vectors like 1, 1, 2, 0, 2, minus 1, and the B vector would be minus 5, 1, 2. Okay, now let's take the multiplication of this. This would be minus 5 plus 1 plus 4, and the other is 0 plus 2 minus 2. Okay, so here it comes 0 and 0. So I got a 0 vector. Okay, so from this we got that the inner product of these subspaces is 0. So from this we can say that these are orthogonal. Okay, so these subspaces are orthogonal. Understood? So that's how we can proceed it for any functions and on any subspaces. Okay, right. Now let's talk about orthonormal vectors. Orthonormal vectors. What are orthonormal vectors? So for that, let's just consider a set S which has vectors like u1, u2 to un. Okay. Now this set is in my inner product vector space. Okay. This is an inner product space. This set is lying in the inner product space. Sorry. Now this set S is said to be orthogonal. This set S is said to be orthogonal if each pair of vectors in S are orthogonal. If each pair of vectors are in S are orthogonal, right? Now, for S to be orthonormal, S is orthonormal. This set is orthonormal if S is orthogonal, S is orthogonal, and each vector in S has unit length. Unit length. Okay. So my set S is orthogonal if each pair of vectors in S are orthogonal. That is what we mean to say, that for the orthogonality, we have ui, uj, that each and every pair of the vector has to be equal to 0 for I not equals to j. Then we will say that my set S is orthogonal. And for the orthonormal, if we have the inner product of ui and uj is equals to 0 and 1. Okay, 0 is for I not equals to j, and this is for I equals to j. I equals to j, that is for ui and similar vectors like u1 comma u1. If it is equals to 1, then we will say it has to be equals to 1 for the same subspaces. Okay, now we can also see that S is orthogonal if S is orthonormal if S is orthogonal, and each vector in S has unit length. Okay, so if there is a vector, let's say we are normalizing u vector. Okay, so for a vector has to be unit length, we can convert it to an orthonormal vector, which is ui upon norm of ui. Okay, and this is said to be normalizing a vector. Normalizing a vector. Now this ui vector has a unit length, or you can say this bi vector is a unit length. Okay, now this set of bi is said to be the set of bi is said to be the orthonormal vectors. Orthonormal vectors. Okay, so this is the condition for orthogonality. That's my vector has to be orthogonal, and also it has a of unit length. The vector is of unit length. So converting any vector to its unit length, we have to divide the vector by its norm. Okay, then this respective result bi, let's say I have taken each and every vector ui and divide it by its norm, then the resultant vector would be my set of orthonormal vectors. So this is the difference between orthogonal and orthonormal. Hope you will get it. Okay, now there are some results in this, which is the first result is that S, the set S is orthogonal set. Orthogonal set. Okay, orthogonal set of non-zero vectors, of non-zero vectors. Then this set S is linearly independent. Okay, we have a set of orthogonal vectors which is like this. S equals let's say u1, u2 to un. Okay, un, we have this set of vectors. Now they are saying that this, if we have an orthogonal set of non-zero vectors, then this set of vector is linearly independent. Let's just see this, that how are they saying is it. So for this set to be linearly independent, the first and very basic condition for any set to be linearly independent, so I will write it into the linear combinations of the vectors. Let's like a1 u1 plus a2 u2 plus going on to an un is equals to 0. Okay, so if I got my all ai's equals to 0, then we will say that these vectors are linearly independent, right? So that's how we check linear independency, right? So let's just check it, that whether all ai's are, all scalars are 0 or not. Okay, so what we will do, let's just take out the inner product of this equation with respect to u1. Okay, okay, so if I'll do this with respect to u1, then what would we get? We will get a1 u1 plus a2 u2 going on to an un, and we are doing its inner product with respect to u1, and that would equals to, we are doing the similarly here we are doing the inner product with 0 here, with the u1 here also. Okay, 0 comma u1. Okay, now we know that any if we multiply any vector to it 0, it will going to be 0 only. Okay, now what will that, now we are going to apply the linear property of the inner product spaces here. So here it would be equals to a1 u1 comma u1 plus a2 u2 comma u1, and similarly going on to an un comma u1. Okay, now if these vectors are orthogonal, if these vectors are orthogonal, then we have studied just now that I can move back, that if ui comma uj is equals to 0 when I not equals to j, and this is equals to 1 if I is equal to j. Okay, so by applying this we can say that this would be equal to 0. Okay, because they are perpendicular to each other, they are orthogonal vectors. So and similarly all the vectors here would be 0, and the vector like a1 u1 u1, this is a1 orthogonal inner product of u1 with respect to u1 would be equal to 0. Okay, now we know that this vector u1 is not equals to 0. Okay, we have considered the set of non-zero vectors, so the inner product of that would not be 0. Okay, so we can say that the a1 would be equal to 0 from here. Okay, so I got my a1 which is equal to 0. Now similarly we can check for other vectors, that if I'll do the inner product with respect to u2, that means all the other vectors would go to 0, and only we have remained is a2, u2 comma u2, and 0 comma u2, and that would mean that a2 z2 comma u2 would be equals to 0, and here also u2 is not equals to 0, so we would say that a2 is equals to 0. Okay, so from this, by applying inner product and inner product on each and every vector, we will got that a1 a2 to an, all my ai's are equals to 0. So from this we can say that S is linearly independent. Okay, S is linearly independent. Understood? Okay, now the second thing in this is a remark. Now the second remark is Pythagoras. Pythagoras. Okay, Pythagoras. Now what does it in it? What is in it? So we are considering same like orthogonal set of vectors, which is u1, u2, u3 to ur. This is my orthogonal set of vectors. Orthogonal set of vectors. Now, by the help of Pythagoras, we are just proving the Pythagoras with the help of inner product and orthogonal set of vectors. It is saying that the norm of u1 plus u2 going on to un r's whole square is equals to norm of u1's whole square plus norm of u2's whole square plus going on to u norm of ur's whole square. Okay, similarly if I'll do it for two vectors, okay, then you can easily see the Pythagoras theorem, which is norm of u plus v's whole square would be equal to norm of u's whole square plus norm of v's whole square. Okay, now see it that how are we saying this? Because let's just see it here, that taking out this vector, this norm of u1 plus u2 to ur. Okay, so what does this mean? We are taking the inner product of u1, the linear combination of like u1 u2 to ur vectors, the sum of these vectors, not linear combination, with itself, that is u1 u2 to ur, and its inner product with u1 u2 to ur. Okay, now what will that be? We will apply the linear property. So that would be u1 comma u1 plus u2 comma u2. Okay, and ur comma ur, and all similarly all those vector where I is not equals to j, that is ui comma uj. All the all the combinations of those vector where I is not equals to j, because they are going to be 0, because the set of orthogonal is the set is of orthogonal vectors. So we know that this is going to be 0, and these remaining vectors can be written in the format of u1's whole square plus u2's whole square going on to ur's whole square. Okay, so this is what for the two vectors. You can also check it for two vectors, that this is my corresponding Pythagoras theorem. So in this we have said that we have checked this, that by the help of inner product spaces we can also see that how does the Pythagoras theorem actually came. Okay, now let's talk about orthogonal bases. Okay, orthogonal bases. Okay, now a basis of subspace is power n. Okay, I'm just considering any vector. A basis of subspace generalized form, that is e's power n. Now this is called orthogonal. Is called orthogonal if the bases of the vectors are orthogonal. If the basis vectors are orthogonal. Are orthogonal. And the base is called orthonormal if the basis vectors are of unit length in addition to orthogonal. Okay, so if the vectors are orthogonal, then they will the vectors of basis is orthogonal, then it is said to be the orthogonal basis. And if the vectors are orthogonal and also of unit length, then these vectors are said to be the orthonormal basis. Orthonormal basis, right? These are the same things, but just that the basis vectors are orthogonal, then they are orthogonal basis. And if it is satisfying the property of orthonormal, then they are orthonormal basis. Okay, so for this, let's just consider this set S, which is u1 1 2 1, u2 let's say 2 1 minus 4, and u3 which is 3 minus 2 1. Okay, and this is an R cube. Okay, now this set of vector u1 u2 u3, they, what are these vectors are orthogonal. You can check it by doing the inner product of these. This is going to be 0. Okay, these vectors are orthogonal. Orthogonal. Okay, so if these vectors are orthogonal, we can say that they are linearly independent. By the previous remark, they are linearly independent. Okay, so they will form a orthogonal basis of R cube. Because all these vectors are orthogonal, we can say that they will form a orthogonal basis of R cube. Okay, now there is another concept, which is if they are forming orthogonal basis of R cube, and there is another vector, let's say V, which is let's give it any value, that is 719, and I want to write this vector V into the linear combination of these ui's vector. That is what we mean to say, that we want to write it V equals to x1 u1 plus x2 u2 plus x3 u3, where we have u1 as 1 to 1, and u2 as 2 1 minus 4, and u3 as 3 minus 2 1, and my v vector is 719. Okay, now what are these vectors are orthogonal. We are saying that these vectors are orthogonal. Okay, so we are going to apply the property of orthogonality to find out the values of these x1 x2 and x3, basically to write this vector into the linear combinations of these orthogonal set of vectors. How will we do that? So we have v. Okay, we have v. So what will we do? Let's just do the inner product of uh, this equation 1. Let's just name it as 1 with respect to u1. Okay, with respect to u1, so we will do v comma u1 plus x1, sorry, equals to x comma, like I'll just expand it in the linear property. You will do it step by step. So it would be u1 comma u1 plus x2 u2 comma u1 plus x3 u3 comma u1. Okay, now these vectors are orthogonal, so they would going to be 0. These vectors are going to be 0. The inner product of these are going to be 0. Okay, now the remaining part is this part. Okay, so that is x1 would be equal to v comma u1 upon u1 comma u1, right? And what would be that? V comma u1, that is the inner product of v vector and u1 vector. That is, I think, 7 plus 1, sorry, 2 plus 9 upon 1 plus 4 plus 1, and just doing the inner product of these. Like I'll do it for 1, which is v comma u1. Okay, that is v is 719, and the other one is 121. Okay, so that would be 7 plus 2 plus 9. Okay, and which is 18, I think. So that would be equals to 18 by 6. So 3. So we got the value of x1 as 3. Similarly, we will do the inner product of the equation with respect to u2. So if we do it with respect to u2, we would get v comma u2 plus, the first will go to 0 because the inner product of u2 with respect to u1 would be 0, plus x2 u2 comma u2 and the third one will also be 0 because then a product of u3 with u2 going to be 0. Okay, so we got the x2 equals to v comma u2 plus u2 comma u2. Okay, and what would be that? This is, I think we have to multiply these taking out the inner product of this v and u2, this one, right? So that would be 14 plus 1 minus 36 upon 4 plus 1 plus 16. Okay, so that would be 15 minus 36 and 4 5. Okay, so that is going to be, I think, minus 1. Okay, so we have also find out the value of x1 and x2, and similarly we can find it for x3. Well, let's say, okay, you by doing the inner product with respect to u3, you can find the value for x3, and you can write this vector into the linear combination like we have got 3 u1 minus u2 plus what would be the value here, u3. Okay, so we have write it down this with the help of inner product. We don't need to solve the equations, we don't need to do anything, we don't need to form the equation. Just by doing the inner product we can write this vector into the linear combination. Okay, so from this there is a theorem which arises, which is like, let u1 u2 to un be the set of orthogonal bases of v, orthogonal bases of v, then any vector v which belong to this vector space can be written in the linear combinations of these orthogonal basis vectors by the help of v comma u1 upon u1 comma u1 into u1 plus v comma u2 upon u2 comma u2 into u2, going on to v comma un upon un comma un into un. Okay, now you can see that what is my x value. We got our x value as v comma u1 upon u1 comma u1 inner product. Similarly we got our x2 value which is v comma u2 upon u2 comma u2. So by the help of this you can easily understood that how are we finding that x1 and x2 value, and how are we generalizing our formula for n orthogonal basis. Okay, now this is a constant term which is a value of xi's or the scalar's value. This is this, let's just name it as ki. This is v comma u1 upon u1 ui comma ui. Let's just generalize it. So this is said to be the Fourier coefficient Fourier coefficient of v with respect to ui. Okay, so this is the Fourier coefficient of v with respect to ui, every scalar. This is said to be the Fourier coefficient of v with respect to ui. So now what we have done? We have done orthogonal basis, we have done orthonormal basis, and we have also seen that how can we write a vector into the form of linear combinations of orthogonal sets of vectors. Okay, now there is another process which is, you might have heard about it, which is Gram Schmidt orthogonalization process. Smith orthogonalization process. Okay, now let's see what is in this. So in this, what is it saying is that we have a set of vector. Let's just consider that v1 comma v2 to vn. We have this set of bases of inner product space v. So this is a set of basis vectors. Okay, now we can use this basis to construct an orthogonal basis. Okay, let's say that we can use this vector to construct an orthogonal basis which is w1 w2 to wn of v, orthogonal basis of V. So we have a basis of inner product space V, which is V1, V2 to Vn. And now what we are doing, we are constructing an orthogonal basis of V, which has also the property of orthogonality. So we are constructing those bases of V. Okay, let's just see how do we do that. So for that, W1 will be equals to V1, okay, and the W2 would be equals to V2 minus V2 comma W1 upon W1 comma W1 into W1, okay, and the third orthogonality would be V3 minus V3 comma W1 upon W1 comma W1 into W1 minus V3 comma W2 upon W2 comma W2 into W2, and similarly going on to Wn, we have Vn minus Vn comma W1 upon W1 comma W1 into W1 minus going on to Vn comma Wn minus 1 upon Wn minus 1 in comma Wn minus 1 into Wn minus 1. Okay, now what are we doing here? The first vector of orthogonal basis would be the V1, okay, and the second vector we would find by V2 minus doing the inner product with respect to W1, okay, and the vt vector would v3 w3 vector would be v3 minus, so there is a procedure that is followed in this, okay. So v3 vector is doing the inner product with respect to w1 and w2, right? For the previous vector we are taking the inner product with respect to the previous vectors that are already previous orthogonal basis of v, that is with respect to w1 and w2, and for w4 that would be equals to v4 minus inner product with respect to that, or you can say that the Fourier coefficient. Yeah, these are the Fourier coefficients, right? Fourier coefficient of v with respect to u1 w1, Fourier coefficient of v3 with respect to w1, this is Fourier coefficient of v3 with respect to w2, okay. So for w4 it would be Fourier coefficient of v4 with respect to w1, similarly Fourier coefficient of with respect to w2 and with respect to w3. That is, if we are trying to find it out for W4, then other three vectors would be considered. We are going to find out the Fourier coefficient for each of these three vectors, okay, and subtract those from the from this vector from V4, okay. So that's what is orthogonalization process is, okay. Okay, so these W1, W2 to Wn, these are my orthogonal vectors, right? Now we can normalize these vector, that means we can convert these vector into the orthonormal vector by Wi cap, this is the new vector, by dividing them by its norm, okay, and this will be my orthonormal set of vectors, orthonormal basis of v, okay. So if we got our orthogonal basis of v, then it is very easy for us to find out the orthonormal basis, because we just need to divide it by the norm, as we need to satisfy the criteria for that it has a unit length, okay. Okay, so now let's you can try this question out, okay. This is based on the Gram Schmidt's orthogonal basis orthogonalization process, sorry, okay. So it is saying that apply the orthogonalization process to find out the orthonormal basis for subspace u of r's power 4 spanned by these vectors, which is v1 1 1 1 1, v2 which is equal to 1 2 4 5, and the other is v3 which is 1 minus 3 minus 4 minus 2, okay. So these are the vectors that we have, these are the bases, and we need to convert them into the orthonormal basis. So before converting them into the normal basis, we just need to find out that what are my orthogonal bases. So what we will do, we will convert them into the orthogonal basis, which is w1 w2 w3, okay. Let's just do that. So w1 would be equal to v1, so that is 1 1 1 1, and the w2 would be equal to v2, which is 1 2 4 5 minus v2 comma w1, v2 comma w1. So that would be v2 comma w1 upon w1 comma w1 into w1. Okay, so that would be 1 2 4 5 minus, what is v2 comma w1? Just find out the inner product of this. This would be 1 2 4 5, 1 plus 2 plus 4 5, that would be 12, I think. And w1 into w1, 1 into 1, 1 into 1, we are finding out the inner product of w1 with respect to w1. So it would be 4 into w1. So that would be equal to, just multiply this. W1 is what? W1 is 1 1 1 1. Okay, so this would be 3. Just subtracted those values and we will got 1 minus 3, like 1 2 4 5 minus 3 3 3 3. Okay, so we will get 1 minus 3 is minus 2, minus 1 1 and 2. Okay, so this is my second vector, orthogonal vector. Okay, what is that third vector? We can also find that third vector, that is v3, 1 minus 3 minus 4 minus 2 minus v3, Fourier coefficient of v3 with respect to w1, that is v3 comma w1 upon w1 comma w1 into w1. Okay, we need to find that out. So what is v3 comma w1? Inner product of this into this, that is, I think this is equals to 1 minus 3 minus 4 minus 2 upon 4, and that would be equals to 4 5 6 7. Okay, this is minus 8 by 4, that would be equals to minus 2 into w1, 1 1 1 1. Okay, minus Fourier coefficient of v3 with respect to w2. Okay, now we are going to do it for w2. Okay, and what will that be? v3 into w2, inner product of these two, like v3 and w2. This is my w2. So what will that? 1 minus 2 plus 3 minus 4 plus 4, sorry, minus 4. Okay, so that would be equals to minus 7, right? So we got minus 7 divided by w2 into w2. We'll have to find out the inner product of this. That would be 4 1 1 4. Okay, that is 10 into w2, that is minus 2 minus 1 1 and 2. So you will need to solve this, that is multiplying these vectors into this constants into this part, similarly multiplying these constants into this part, and you will get your third vector also. Okay, so whatever be the result here for this, by just you just need to do some addition and multiplication and subtraction here. Now we got our orthogonal basis, okay, which is this one and this one. Now we need to convert them into orthonormal basis. So what will we do? That wi cap, this is orthogonal set of vectors, would be equal to wi upon norm of wi. So I will do it for w1. So the orthogonal it for it would be wi cap would be wi, that is 1 1 1 1. And what is the norm of w1? w1, the norm of w1 would be norm of w1's whole square is equals to 4. So the norm of it for it is w1 equal to root 4, that is equals to 2. We know that how to find the norm. It is just the root 1 square plus 1 square plus 1 square plus 1 square. Okay, so that is equals to 2. So this is my 1 by 2 1 by 2 1 by 2 1 by 2. So this is my orthonormal basis, orthonormal vector. Okay, similarly you can find it for w2 and w3. Okay, no need to do anything in that, just need to do some calculations and you need to know the process of it. Okay, now we know orthogonal matrix. Orthogonal matrix. Okay, what is orthogonal matrix? We all have studied this, that the orthogonal matrix is P transpose P equals to identity. This is my orthogonal matrix. Now, if we need to know that whether a matrix is orthogonal or not, the first criteria is this, but you can also check it with the help of inner product like this, that let's say if you have matrix like A1, B1, C1, A2, B2, C2, A3, B3, C3. Okay. Now consider this matrix into the vector format. Let's say this is my U1 vector, this is my U2 vector, and this is my U3 vector. Okay. We have converted this matrix into the vectors format. So if Ui Uj is equal to 0 for I not equals to j, and Ui Uj equals to 1 for I equal to j. Okay, then we say that the matrix is orthogonal. Okay, that's what the orthogonal property is. Okay, so basically if a1 square plus a2 square plus a3 square is equals to 1, and the other is multiplication, which is a1 b1 plus a2 b2 plus a3 b3 is equal to 0. Similarly, you will do it the other combinations too. So if this is the property they are following, then we would say that this is my orthogonal matrix. So this is the criteria for checking whether a matrix is orthogonal or not. You can check that. Okay, so I think this is enough for the orthogonality. That's all about orthogonality. Let's meet in another lecture. Thank you for now. Bye.